So Elad BARAM is the Vice President of Products on Emza Visual Sense. Elad BARAM has a background as a product manager at SanDisk and has served in similar product leadership positions in high-tech startups specializing in consumer and automotive markets. He holds a Bachelor of Science in Communication System Engineering from Ben Gurion University of the Negev in Israel.
Yeah.
Please go ahead and present Elad.
Thank you. Thanks everyone for joining the talk. So this talk is actually a little bit different in the sense that it's give you an overview of a journey of a deployment, a real use case, real application, and deployment into mass production of TinyML in the vision space. So I think that TinyML has been catching up very nicely in the traditional sensors and in the audio space, but in the computer vision, we have not seen deployment in the magnitude of millions of units yet. And I believe that this application actually is getting there, and we want to share our story and experience with the audience here. So just 30 seconds on who we are. So Emza Visual Sense has been around for a while, since 2006, was doing computer vision on the edge all the time. And we are basically a full solution provider. So we are doing the algorithm, hardware, software, system integration. We have been acquired by Himax Technology. Himax Technology is a NASDAQ traded company that is pretty well known in the TinyML community for its ultra low power vision sensor. So today we are basically the vision part of the Himax Technology family. So our story really begins in CES 2019 when Intel announced Project Athena. And Project Athena was kind of the next generation of innovation around the personal compute and laptop. And the intention was that to make the laptop really smart, and you can see some of the wordings here around human understandings, worry-free day of battery life, artificial intelligence. Everything here is kind of around context awareness. The question was really how to put it in play and how to enable real value. So the first thing that we did is we tried to map what is doable and what exists in the landscape of the personal compute. And I think we can kind of see the view that on the x-axis, you see how sophisticated the sensors are. And on the y-axis, you can see the sensing power and the compute power. And basically, you can do a lot of amazing things with software solution that is running on the laptop, including identities, emotion. You can do all of that stuff. The issue here is that it consumes a lot of power, and it's also in a non-private domain, meaning that the user needs to opt into the fact that they are being filmed all the time, and footage is being taken all the time. Our concept was that if we can bring some sort of a TinyML vision and actually make a computer vision in the sensory domain, and in the sensory domain, it means you're on a very low power, basically on the milliwatt scale, and you are not doing any processing on the main processor. So everything is happening right next to the camera. And then you are using the pixel, but you are still within the privacy domain. There is no image that is going out and nowhere. And then we can start to enable some interesting use cases. So the first use cases that were introduced is actually Wacom approach. Like we all know that basically for a mobile phone, you never wait for your mobile phone, but when you're approaching your laptop, you need to open it, you need to log in and all the password. It's kind of a drag on eventually on the user experience. And you may think, can it work like a magic that you're just approaching the laptop and it's automatically waking up and recognize you with the Windows Hello. So you need a wake up sensor and walk away lock. So again, if you are in a coffee shop or in the office or at home, today, most of the users, they actually never change the 5-minute default. So you walk away and the laptop continue to work, the display is on, someone else can actually look on the data. So providing to the machine the understanding of what's the context of the user, is the user is there or not, approaching, walking, you can actually improve a lot the user experience, both on the usability side and also on the security and the power saving. So that's kind of a short video clip with CES 2020, which was still happening in Vegas. And you can see as you are approaching, and by the time you are sitting in front of the laptop, actually you're already logged in. So it's a combination of a computer vision sensor that is doing face detection, waking up the system for modern standby, and then the Windows Hello by Microsoft is actually making face recognition. You combine all of this together, you are getting this immediate, instantaneous login. So that's kind of an example, but you can take actually the concept even further, because if you are making detection of one face, maybe you can detect another face, and that brings you into the area of kind of contextual understanding and contextual security, because if someone is speaking behind your shoulder, you can now actively do stuff. I mean, you can dim the screen, you can blur the screen, you can just have a pop-up notification. But in the public domain, if someone is walking and someone is looking behind, it can be a nice feature if you can actually let the user that someone is actually looking on the display just above each shoulder. So that's improving the security. But even bigger promise was actually on the power domain. So one of the biggest issue with laptops, of course, is that you need to take a charger with you. And one of the biggest consumers of power in the laptop is the display. But it turns out that big portion of the time as a user, when you are in front of the laptop, you are not really engaged with the content. I mean, when maybe you are speaking with a colleague, or you are just going for 1 minute to the kitchen, or you are doing Facebook, whatever you are doing, there is big chunk of the time that you actually not engaging with the display at all. Now, in a mobile phone, it's pretty easy because they are using the accelerometer as kind of indication whether the device is in usage or not. But for laptop, it's a stationary device. It stands on the table all the time. And if you actually want to leverage the user attention to save power, you need to have some sort of face detection and user attention indication. But that, of course, makes the algorithm much more complex, because this is not only whether there is a human or not. This is now bringing the concept of attention detection. So what is the proposal in terms of the engineering of it, not the algorithmical piece of it? Our idea was basically to take a chip, which we call WiseEye1. I will describe it in a second. And in every laptop, behind the glass, there is a small PCB that is the camera module. And the idea was to have this inference engine right next to the camera, taking a low resolution image out of the camera, and having all the face detection and the other algorithms basically running on the board, and reporting to the operating system only metadata around whether user is present or not. So it's very secure in the terms that there is no hardware interface that can take the image out at all. So so user can be relaxed that in terms of privacy, image can never leave the camera module. There is no hardware interface to it, and the user experience will be much better as the laptop now understand what the user is actually doing. So in terms of the real world challenges, so the issue here is that you have a tiny controller, but there is a very aggressive requirement of the distance, the field of view, the execution speed, faces in the wild, which I explained what it is, and engagement level, and so on. So if you can see here, what the requirement in this slide, it shows that we have put ourselves targets to detect in between 25 to 2 meters. And you can see faces in like 25 to 2 meter, how big the difference in terms of pixels are. So it's you need, and this is what for folks that are doing computer vision, so it means that you need to process it in multiple scales. When you need to process in multiple scales, it's become a big issue for microcontrollers, because that's a computational heavy operation. So that the distance is one challenge, and we need fairly wide field of view, processing speed of about 8 to 10 frames per second. And why is that? Because this is not something that is doing analytics. This is something that actually interacts constantly with the user. So if we are in the adaptive dimming, if we are now dimming the display, because I'm like I'm now looking aside, but when you look back, you need immediately the intensity to go up. So actually you need the response time that would be about 100 millisecond response time. So all this type of processing needs to happen on a tiny microcontroller, which is very hard. And we wanted to extract the bounding boxes because the location of the face has a meaning. And also based on the bounding boxes, you can extract distance estimation. So that's also a very important parameter. So it ended up that this is not really a classification problem. It's actually an object detection problem, as we needed a bounding box for the user distance and everything. But we are running on a less than 2 megabyte SRAM MCU, 400 megahertz. We couldn't run any sort of an classical like SSD type of detection if we wanted to combine everything. And we were playing a lot with MobileNet V1, V2, and scaling it down and up. Nothing eventually converged on a pure NN scheme. Nothing really converged to be able to execute in the right speed on this processor. So eventually, the scheme that we have brought to production is working in 2 stages. So the stage 1 is actually a detection that we are doing with a very fast detector with a classical ML, sort of boosted trees. The good attributes for those detectors that they have a very fast rejection. So you can identify very easily where are the areas of interest in the images. And then we are using NNs as a second stage for the classification, which are more accurate. And here we have kind of a 3-state, whether it's a face or a head, or just a noise. So we are using the second stage CNN as kind of as augmentation to get to a better better true positive and to reduce some of the false negative. But with this scheme, we actually managed to get to meet all of the requirements of working in multiple scale with big distances and run it in a few frames per second that will be very responsive to the user. So we kind of developing the algorithm and everything seems okay. You can see here in this video that is running, we're getting the image and there is a bounding box and there is a yaw estimation. Everything seems to be working nice and ready. But then COVID-19 is coming. And suddenly everyone is with facial mask. And not only that, all the people that are doing the evaluation with our customers, they are evaluating it with facial mask. So we had our own emergency response to COVID-19, which we had to generate thousands and tens of thousands of images with faces with masks. Now, back then at the beginning of COVID, you couldn't really find. So what you see here, basically, everything is augmentation. Like 99% of our data set was actually augmentation of masks that were planned on a very strong network on the cloud. But we were creating this data set to train the embedded model to recognize people with facial masks. And we got almost to the same detection rate of faces with mask and without mask. So that was the first thing. Now, the second issue is the variety of the real world, because when you are running benchmark like Coco and VIP and all of those faces in the public data sets, most of the people will be kind of centered in the image, smiling to the camera. That's very nice. But the reality is that people are sitting hours in front of the laptop, and then the yaw angles are much on a bigger range. The pitch angle also are much on and people are doing like that. And what we have been seeing is that the algorithm is starting to degrade because actually the faces are not full faces. People are covering some of the faces. So we had to enrich, and that was a massive data science work actually, to enrich the data set to be able to work in real life conditions. So just the harvesting some data sets from the public domain was not enough. We had to use our own, generate a lot of data about ourselves. Now, another big barrier is actually the illumination condition. And it's not specifically the lux. I mean, people tend to think of problem of computer vision in terms of darkness versus full sunlight on the extreme. But the real issues are the dynamic range, and I'll explain. People tend to think of images as what they experience on their iPhones. But what you're experiencing on the iPhone is something that is to start with, the image sensor itself is by far on a higher quality than like what you typically find on a laptop in terms of resolution and the size of the sensor and so on. And more than that, as a user, you are seeing an image that is being processed with a very strong AI algorithm with multiple exposure in order to actually get the image to be very nice. But what you see here in these slides, this is how a raw data looks when you get like kind of, I wouldn't say it's not a simple sensor, but it's a typical grade of image sensor that is being used in a laptop. But how it looks like when you're only doing the mosaicing before you have a strong ISP. And this is the case for TinyML, because if we would take the image after the ISP, then the power would be significantly higher. So you're in a situation where you actually have a fairly low quality images. The algorithms need to be very strong, and you're running them on a TinyML processor. So it's a very challenging problem to solve. We had to develop some special algorithms to cope with it, and you can see that when we say HDR, so it's either if there is a strong sun or illumination behind the faces, then the face is completely dark. On the other end, if the room is dark and the only illumination is coming from the display, then the face becoming very, very white. You're almost losing all the facial landmarks because of the reflection of the face back to the camera. So these issues are pretty complex to solve in terms of dealing with the sensor and so on. I want to say maybe just one slide on the hardware itself. So we have been working with WiseEye1, which is a chip that I'll show it in a second. It's so small, I hope that you can see it actually in the video, but it's very small, so it can actually fit into a narrow bezel design. But it also has a unique core to do always-on motion detection, because one of the important things, and many of the lectures here on the TinyML is how do you actually running on a few milliwatt to trigger the system. So in this chip, we have a specific circuit that actually without any CPU, everything is a gate level implementation that you can get the image, compare it to the previous image, have some sort of different sensitivity levels, and be able to decide on a gate level implementation whether you actually need to wake up the CPU to start to do inference or not. So that's the only way today that exists basically to do some sort of motion detection. And this is important because when the laptop is in a modern standby situation, we need to be just on a few milliwatt power to be able to wake up the entire system. So it's a pretty unique chip. Now, the way it actually looks like, this tiny PCB that you can see here and under the tip of the pencil, this is actually the WiseEye chip. And here you can see the camera sensor. This is a 2.2 millimeter design. I can try and hopefully be able to show you here I don't know if it will be able to focus, but that's how it's more. I mean, it's really amazing piece of engineering when you think of it. It's so small and it has optics, electronics, AI, inference engines, everything in just a 2 millimeter form factor. So I think it's pretty impressive piece of engineering that is going to be deployed in millions actually in the next few months. And so to conclude, we have shown that we could trace and identify the opportunity basically to take TinyML and to bring it into deployment in millions of devices, bring it to the right power envelope, to the right cost structure, and bring value to consumer by applying TinyML. Now, having a demo is always easy. The problem is to getting into production. It's a lot of work. Need to do lots of optimization. It's tiring work, but I think that's what it requires in order to get into the robustness to deal with the real life situation. And we think that we are really in the early life of adoption, because what the chip that we are using today is great, but I know what we're going to use for the next generation. It's going to be 50 times faster. So with the advancements of both on the silicon IP and the NPUs that are coming in the next year, the stuff that we will be able to do in computer vision, in the TinyML, will be amazing, and we see this goes to many more verticals in the consumer electronic space. So we are very happy to be in this emerging world of smart devices and enable these capabilities in the consumer electronic space. So I think that concludes my talk for today.
Thank you a lot, Elad. It was really, really interesting. And I also think it's really practical and seems to be an extremely valuable use case. So you touched on that at the end of the presentation. So it were very intriguing to see, what kind of applications that come out of this technology. Yeah. So on the question, there is one that's asking how fast is your models? And I then believe it's the sort of full loop through there.
Yeah, so I think that we are running a full circle somewhere in between 200 milliseconds. It's, I would say, 150 to 300. This is depend how many objects. I mean, this is not really deterministic, but I would say that the stage 1 is running in about 150 milliseconds. I mean, the boosted rescanning everything. And if needed to get to the second stage of the NN, so this is adding today about 60 to 80 milliseconds, but it's not, there is no straight answer here, because there are a few models that we are using, and also it depends whether we are running the native reference kernel for TensorFlow, or we are running it with the Synopsys MLI. We can even run it with the Edge Impulse compiler. So there are few different implementation, but I would say that it's 150 to 250 is kind of the range of all included full frame coverage with bounding boxes out.
Okay, great.
And Thomas, also, if I may ask.
Yes, sure, Evgeny, go ahead and ask.
Yeah, so I think it's been quite a journey, Elad, and I really appreciate you sharing all your experience with the audience, because I think it's like you said, developing a demo is one thing, but developing a product, it's like it takes much more. I think your practical insight is really important, and by the way, congratulations. I think this journey is coming to fruition now. Two questions related to the practical angle. I think one, you mentioned 20% battery improvement if you use your technology. What kind of data of use model you assume for this? How do people use the device to get the 20% battery improvement? That's one question. And second question, related to data sets, because we all know that data sets are extremely important to develop any kind of TinyML models. And you show a couple of interesting corner cases with light and people doing kind of different poses and the mask. Kind of from your experience, from Emza experience, how much data you need, both positive, negative images, to really develop this production quality models, not demo quality models, but production quality models?
Okay, so for the first question, so actually the usage model was developed by Intel, and according to the Intel, again, I'll throw it verbally. I don't. It's kind of it's information that I'm not sure it's fully on their website or not, but I would say that generally speaking, they divide the world in a way that about half of the time when you are in front of the laptop, you are not truly engaged with the content. It means that what it's called like less than 5 minutes of unengagement. I mean, if you're going for more than 5 minutes, anyway, the system will turn it off. So that's not an issue. But there is about 30% of the time that it's a non-engagement for less than 5 minutes. And under these 30% of the time, this is the opportunity to reduce the display intensity. Now, just to understand, the display intensity is something that is between 1.5 watt to a very expensive display, low power display, to 3 to 4 watt in a mainstream display. So you are investing 50 milliwatt of active inference to save about, in average, 2 watt of display intensity, if you can actually recognize that the person is now chatting or doing something else and not actually looking on the display. So that was the usage model that was actually modeled originally by the Intel usability team. Now, regarding the data set, yeah, that's maybe the biggest challenge that we had. I didn't mention, but another item here is that on the public data set, usually those are full HD color images, and the real sensor that we are using like a QQHD. So the amount of pixel is much smaller. We have been just taking lots of videos on our own as a project of generating data. And then if you have hours of videos, so those are basically thousands of frames, we need magnitude of tens of thousands of images in order to properly train the models. I think the numbers is tens of thousands to properly train. Below that, it wouldn't cut it. Now, also again, because there are two stages, so in the CNN, you can do some transfer learning, so then maybe you can have a little bit below. On the boosted tree, we need tens of thousands of images.
Thank you. Evgeny, what do you think? Should we stop there or take some more questions?
I think there's one more question. I think today we are kind of going a little bit wild. We are compromising.
Actually, Thomas, if I have time, I also had one question.
Okay, go ahead.
We
are trading interactivity for engagement. So
it's not related. Well, it's related to what Elad just presented. But Elad, did you guys construct a data set with the people wearing masks? Is it something that you will be able to share the data set with the masks? Because quite frankly, people working in facial detection, facial recognition, I think will have to adapt their training sets now.
Yeah, well, we need to consider if we want to release it as to the public domain as a full data set. I mean, we invested a lot of energy there, and by the way, on the course of doing it, so because lots of it was augmentation, we encountered some issues of overfitting. So the first round, we had then to find another augmentation with different type of mask, because the variety of the mask was not enough. I mean, at the start, everyone was using the same mask, but then suddenly even the mask became like a fashion item, and so
yeah. That's what I was wondering about. Okay.
That was a big deal, but we can. I can check with you offline, and we can consider if we'll actually release a data set to the public domain.
Thank you, Elad. I appreciate it.
Can I just chip in as well? I've been thoroughly enjoying Elad because of the fact that we do audio and sound detection, which again is a kind of, it's not the standard thing that people do with audio, because there's much effort been gone into speech, understandably. And it seems like your journey's been very similar to ours, that the actual capture equipment is not quite as pure and clean as you might like it to be, and that the capture that you make is more challenging and difficult than you think, and augmentation turns out to be more challenging and difficult than you initially think. So it's good to hear that other people are experiencing the same kinds of challenges when they're trying to do this level of production, that it works reliably all the time everywhere.
Yeah, I think there is always, I can summarize it, that there is always this gap between it's working perfectly on the PC, but it's not as good on the embedded side when you take it to the embedded, and then how you need to invest a lot of work to get the embedded implementation work as good as whatever working on the simulation on the PC side. So Yeah. I think everyone that is doing it real life deployment, encountering this journey.
Okay, maybe at this point I should take the steering wheel over. Thank you, Thomas, and thank you, Elad.
Thank you.
It's been a great session.
Of course, I do want to thank all our sponsors. So the premier sponsor, Newton, with their automated TinyML solutions. Executive sponsors, ARM, and we organized also a very nice panel that we witnessed just now. Edge Impulse as well. Jan was there and presented some of their work just now as well. Then also Qualcomm, working on advancing AI research to make efficient AI ubiquitous. Sentient, working on chip solutions to do ultra low power, high performance, deep neural network processors. Then our platinum sponsors, Infineon, we've had a keynote from Wolfgang from Infineon earlier today. Reality AI, working on advanced sensing with Edge AI and TinyML. Then our gold sponsors, Latent AI, working on adaptive AI for the intelligent edge. SensiML, building smart IoT sensor devices from data. And then our silver sponsors, Emza, where Elad also presented today what they are up to, Green Waves Technologies, HOTG, Imagimop, Kisho, Seed, and ST. And with that, that's the wrap for today. Thank you everyone for your attention and your attendance.